Hi everyone, welcome back to the Technion's ECE Deep Learning course. I'm Tal, I'm the instructor in this course, and in this course we are going to build the idea of deep learning from scratch, learning the basic blocks, and we begin with talking about optimization concepts, which is what we will do in this tutorial and in the next one. And the goal in mind is to design optimizers for neural networks. We'll talk about neural networks later in the course. And this is what we're going to do today and in the next tutorial. Okay, so let's jump right in. And here I am. So if you haven't watched the recap tutorials, then I'll give you a short overview of the format, of the structure of the tutorials. And we will be working with Jupyter notebooks, which is what you see right on the screen. And the idea is that we can use both theory, math, and code all in the same place. So this is really good. And if you want to set this up locally, there are instruction to do this on the web, on Moodle, and on the GitHub of this course. And if you don't want to work locally, then you can just run these notebooks on Google Colab or any other notebooks provider. You can see instructions on GitHub. So in each notebook, we will have an agenda, right? What we are going to talk about, the topics. And today, in this tutorial, we are going to cover the first part of the optimization, which might not be that new to you. But towards the end, we will talk about learning rate scheduling or annealing. And this might be new to you if you're just finished the machine learning basic course. And in the next tutorial, we'll talk about more advanced stuff. So this will be we will talk about optimizers. And this will be what we are going to use when we optimize neural networks. At the end of each tutorial, we will have recommended videos. So these are just links to YouTube videos from across the web on topics discussed in this tutorial. And finally, under the credits section, you can find relevant references if you want to dive deeper into the concepts we discussed in the tutorial. Okay, so let's begin. And before we dive into the deeper concepts, let's warm up with some basic blocks. And the first one is discussing unimodal versus multimodal optimization. And basically, we're going to talk about the structure of functions. So what are unimodal or multimodal functions? So unimodal functions, they are functions that have only one optimum. That means that the local optimum is also the global, and it looks something like this. Now, if this looks familiar and what comes to your mind is convex functions, then your intuition is correct, and we will talk about this in a minute. The next type of function is the multimodal functions, and that means that they have more than one optimum, and it looks like this egg tray here, you can see. And basically, this is what we will probably meet in real life. So the functions will have more than one optimum. But most algorithms or search schemes, they are based on the assumption of a unimodal surface because they assume that you can find a global optimum. But this is not always true. And the optimum that we find is usually something called the local optimum. And the best thing we can do is find the global optimum. So how can we do this? We will discuss this in this tutorial. So the global optimum is the best of all local optimum designs. Now, in practice, we apply these algorithms, these search algorithms, anyways, without thinking about unimodality. And what we're going to talk about is now the relation of these unimodal and multimodal functions to convexity, which is probably what you have seen in previous courses. So what is convexity? So it's better illustrated in this drawing here, and maybe let's just jump to the board and try to draw this ourselves. So what does it mean to have convex functions? So here, we have this curve here. And we want to understand if it's convex or the other side of convex is concave, and so the definition will be inverse. But let's talk about convex functions. So convex functions. So let's take 2 points, x1, just right here, and x2. Now let's apply our function to these points, and we get, if we go to the function, we'll get this one, so f of x1, and pardon my drawing skills, and this will be f of x2. We are trying to characterize this function. So what we're going to do now is we're going to draw a line. Okay, what does it mean to draw a line? So we're going to draw this line here, the line that connects the two points. And mathematically, this means the following. So if you recall the line equation, so let's pick a t, where t goes from is a value between 0 and 1, and we multiply it by f of x1, and we take the other side of this line, which is 1 minus t, multiplied by f of x2. Now this is the line that connects the 2 points. So this is what we draw here. Now convexity means that first of all, if we set this term to 0, then we get something called the line equation. So you can move the terms to the side and find the line equation. But this is not what I'm trying to tell you here. So what this means is that if you want to understand, if you want to say this function is convex, then the line that connects these 2 points, it should be above, okay, the line that the function applied over the line that connects these 2 points. So what does this mean? It means that it means applying f on the line that connects these 2 points. So t multiplied by x1 plus 1 minus t multiplied by x2. Now, where does this located? Where is this located? So this is exactly this part, this area here. So this is the function where t goes between 0 and 1. So when t is 0, then we are at f of x2 or x2. And when t is 1, so this part goes, then we are at the beginning of the line, right? So, and in between, we are traversing this line here. Okay, so convexity means that the line that connects the function applied over each point separately is always above the line, the function applied over all the points on the line between x1 and x2. Okay, great. So let's go back to the notebook. And in 2D, it means that the line that connects every 2 points is always within the region of the function. Okay, so it doesn't go out. So in concave functions, the two points in the region can actually go outside the region of the function. And this means the function is concave. Now, why is this interesting to us, and why all this discussion about convex functions? So here is the idea. Convex functions are unimodal. And why is this interesting? Because remember that unimodal functions, they have only one optimum, and the local optimum is also the global one, right? However, unimodality is a stronger assumption than convex function. And the other side, the other statement is not true. So unimodal functions are not always convex, but they are usually still easy to optimize. So as I just said, unimodality is a stronger assumption. Now, In this course, we don't talk about unimodality and multimodality anymore. We are just going to talk about convex functions. And most of our derivations, at least in the lectures, in the theory part of this course, will be assuming convex functions. Okay. Now, unimodal polygons, as I just said, do not need to be, need not be convex functions, and this is beyond the scope of this course. Okay. So what conditions are required for optimality, right? So we're interested in finding the optimum of some functions. Later in this course, we will talk about loss functions or cost functions, and we will want to find the values that minimize a loss function or minimize a cost function. So this is why we are interested in the optimum. And let's discuss the conditions that are required for optimality. So let's take an f. F is a function that takes us from Rd, dimension d, to some scalar r. Okay, so the gradient. So you've probably met this before. And one thing that comes to mind is, first of all, what is the dimension of the gradient? So the dimension of the gradient is the same dimension of the input. So this means that the gradient is in Rd. And so usually people get confused with the gradient and some other mathematical term, which is called the Jacobian. So let's just stand on the difference between these two, and then we continue. So what is the difference between a Jacobian and a gradient? So gradient is defined for functions that take us from Rd to R, so it's just a single dimension. And as we just said, the gradient is in Rd as well. And it looks like this. So it's a vector where each cell, each input in the vector is the partial gradient of f with respect to the one of the components. So x1 till xd, the final term in the input vector. Now, what is a Jacobian? So the Jacobian is a more general term, and it's defined for functions that take us from Rd to Rm. And this makes the Jacobian a matrix. So the shape of this matrix, the dimensions are Rm on D. So it's a matrix. So let's just emphasize this M here. And basically when M equals 1, then we resort back to the gradient, right? And otherwise we just have a matrix. So we'll talk about Jacobians later in this course. Basically in neural networks, we have something called backpropagation, which is the process of propagating gradients. And we will see that we have some trick to calculate these without actually calculating the Jacobian, since we have matrix multiplications all over the network. So usually we would get Jacobians, but we have some tricks that we can use to only care about the gradient. So we'll talk about that later in the course, but this is the difference between Jacobian and gradient. Okay, so let's say we found some local optimum. So that means the gradient was zeroed. And now we, in order to understand what this, what kind of optimum it is, we are going to look at something called the Hessian matrix. And this is a matrix which is d by d. And basically this matrix includes all the second partial derivatives. So on the diagonal we'll get the second derivatives with respect to some component of the vector. And on the other terms are the partial derivatives with respect to each pair of input variables. Okay, so what does the Hessian matrix tells us? So here is what you've seen in the lecture probably. So if the Hessian matrix is positive definite, that means that all eigenvalues are positive at x0, then we get a local optimum. This is the drawing on the illustration on the left here. If all the eigenvalues are negative, so we say that the matrix is negative definite, and this means that xfs is a local maximum. And otherwise, if we have both positive and negative eigenvalues, then it means we are at a saddle point. Okay, now if we look at the Hessian matrix, and you can see that we have these terms here that might look like the Hessian is symmetric, but it's not always true. In order for the Hessian matrix to be symmetric, then the second partial derivatives should be continuous. And this is not always true, but in this course, we are going to assume that the Hessian matrix is symmetric. This is going to make our life much more simple. Now, if you're interested in understanding this kind of statement, then please check out the Schwarz theorem on Wikipedia. Okay. Now, the next thing we're going to discuss is we have the gradient. We understood that we are interested in the gradient, but what are we going to do with it? So, how are we going to actually find this x0? So we have something called gradient descent, and the idea is that once we calculate the gradient, we now have the direction where the optimum should be, and we want to go in that direction. Now the idea is that we are going to find this optimum using an iterative process, where in each iteration we are taking a step towards the optimum, and the idea is to finally the idea is to minimize some cost function. Now, why do we need to do this iteratively? Why not just one step, just analytically calculate the gradient, set it to 0, and find x0? Then the answer is that it's not always possible. Sometimes this involves inverting a matrix, as in the case for linear regression, as you've probably seen in the previous in the recap tutorials. And some other times it's not always about the invertibility. It can be sometimes that we cannot when setting the gradient to 0, this involves a lot of calculations, and it's just computationally impossible to calculate it. So we want to do this in steps, and gradient descent is an idea that works really well. And in fact, most of the algorithms we are going to see are based on the idea of gradient descent. So this is why it's important to understand how it works and why it works. The idea of gradient descent is to measure the local gradient error function with regards to our parameters or our weights. And then we are going to go down and not up. Going up is called gradient ascent in the direction of the descending gradient. Now, hopefully, once the gradient is 0, the minimum is reached, and we say that we have converged. Now, let me ask you this. So, does that happen in practice? I mean, when we apply gradient descent, do we actually get to an area where the gradient is 0? So, in simple problems, this is actually possible. But this is not what we're going to usually see. And if you're interested in inputs of high dimensions, then, so for example, images, think about images, then we usually won't see that. Now, something interesting happens. So in neural networks or in deep neural networks, what the focus of this course, sometimes when we look at the gradient and we're going to apply gradient descent over a lot of parameters, then sometimes the gradients go to 0. But this is usually a red flag. This is not good. This is a sign of a problem called a vanishing gradient. And usually it's not good. And we will discuss this later in the course and how we can rectify it. So how does gradient descent work? So we have this pseudocode here. You've seen this before in the machine learning course and in the recap tutorials. And the idea is that we are going to use we need to input some hyperparameters to choose some hyperparameters. The first one is the learning rate. And the learning rate is going to be denoted with alpha or sometimes eta, the Greek letters. Now, we choose the learning rate, and this is the step size we're going to take in each iteration. We also initialize our weight vector, our parameters we are interested in, the parameters that are going to lead us to the optimal solution. So basically, when we talk about search algorithms, we are searching for the optimal parameters. In our case, we are going to denote these parameters with W or theta later. And now it's written here that we need to initialize it. And this simple line has a lot behind it. And finding the correct linear rate, the correct initialization is sort of an art. And there are many types and techniques to initialize these parameters. It's not that important in simple problems, but when we'll talk about neural networks that have a lot of parameters, and we'll see that initialization have a lot of impact on the training process and the training dynamics. And for now, we are going to initialize it with something simple. So for example, we can just initialize it with zeros, but we can also initialize it by randomly sampling from Gaussian or normal distribution, the unit Gaussian. But later in the course, we'll see more advanced techniques. Now here we go with the iteration. So while we stopping criterion not met, so what is the stopping criterion? We will also talk about this later in the course, but you can think of some max iteration threshold, or maybe some epsilon difference between the previous iterations. So until we are not meeting the stopping criterion, we compute the gradient. So basically, we take the derivative with respect to W of our f and set this as our gradient, and then we apply the update by going in steps. Notice that we are going in the descending direction, so it's minus learning rate multiplied by the gradient. Okay, cool. And so this looks something like this. Okay, so basically remember that while we hope to optimize convex functions, this is usually not true, and we can get stuck in the local optimum. But ideally, we would reach the global optimum, which is right here. Now, what is guaranteed to us in gradient descent? So not that much actually. And when the cost function is convex and the slope doesn't change abruptly, then gradient descent, we are also going to refer to this algorithm as batch gradient descent, with a small enough fixed learning rate, will eventually converge to the optimal solution. But the time to reach the convergence point is dependent on the rate. So as you can see, there is not much that is guaranteed to us, and we usually are going to deal with non-convex functions. So basically, it's nice to have this convergence idea, but practically we don't have these kind of functions. Okay, so you can see here an example of the learning process. So we can see that we have different initialization points, and depending on the initializations and the step size, we can get stuck in a local optimum. You can see at the top here, or we can take a lot of time to reach the local optimum, or we can get the best initialization and be initialized really close to the global optimum. But this is just plain luck, so we can guarantee it. So this was batch gradient descent, but in practice, notice that according to this term here, we need so we have our data x, and we need to calculate the gradient of w of our parameters, of our weights, with respect to all of the data. So you can see this is the line here, but it might be problematic. So the main problem with batch gradient descent is that it requires us to calculate the gradient over the whole training set. And what if, especially in the case of deep learning, what if the training set is huge? Okay, so deep learning thrives when we have a lot of data, or each sample in the data has a lot of features. So think about images. So if each pixel is a feature, then images of larger resolutions can have a lot of features. So computing the gradient can also be costly. So computing the gradient in this case can take a very long time, especially in the case of deep learning, where we both have a lot of data, and each data point is of very high dimension. So here comes the idea of stochastic gradient descent, SGD in short, or what we will refer to usually as something called mini batch gradient descent. And the idea is that instead of calculating the gradient over the entire dataset, we are just going to sample one instance of a couple of instances, and then we turn to mini batch and calculate the gradient on this sample at every step instead of calculating over the entire data. Now, this is very similar to the perceptron algorithm, which we covered in the recap tutorial. So the perceptron is trained such that we randomly sample one sample, calculate the update rule, and then do this iteratively until we get to some stopping criterion. Now, what is the problem with doing this kind of optimization? It makes the algorithm much faster because we calculate the gradient over a very few samples, but it's going to add a lot of randomness, and this is why the algorithm is called stochastic, because of the randomness. And due to its randomness, it is much less stable. Instead of steady decreasing, which is what happens in batch gradient descent, until reaching the minimum, the cost function will bounce up and down, decreasing only on average. And with time, it will get very close to the minimum, but once it is around the minimum, it will continue to bounce around because we always calculate the gradient over a portion of the data. So we don't get an idea if we are at the minimum or not. Now, when we have outliers, so these are points that are usually noisy and are not, and they are not really, and they should not really be part of the data. And we calculate our gradient on these outliers. Then the step we are going to take, is going to take us in the direction of the outliers, which is it's bad, okay, because it's misleading and it leads us away from the minimum. So this makes the final parameters good but not optimal. In order to actually get the optimal parameters, we are going to do something called annealing or learning rate scheduling. We'll talk about this towards the end of this tutorial. Now, this kind of behavior looks like it's bad. So this randomness looks like it's bad, but actually it's not always the case. Okay, so this randomness can actually help us. Now recall that in practice we are not optimizing convex functions. We are going to deal with very complex functions which are very far from convex, and they're going to have a lot of local optimums, and ideally we want to reach the global optimum. So this added stochasticity, this added randomness, can actually help us escape local minima because we calculate the gradient over a small portion of the data. So let me illustrate this to you. Okay. So let's see. Here is our function, and if we initialize our parameters right here, and then we calculate the gradient over the entire data, then we should get exactly the directions that points toward the closest global minimum, local minimum. So this will take us here, and then the gradient, the slope here is 0, and this means we can stop the optimization because there is nowhere else to go. We calculate the gradient over the entire data, so there's nowhere else to go. But what happens if you still initialize here, but you calculate it instead of on the entire data on some portion of a mini batch of samples, and in the worst case you can calculate it on a batch of size 1. So this makes the algorithm called SGD, stochastic gradient descent. So then we'll have something very noisy. So we can get here, then go here, then go here, then go here, then go here. And actually this randomness can help us escape the global minimum. Because of this noisiness, we can bounce up and down. And we can actually escape this area because we don't rely on the entire sample, on the entire dataset. So basically, we can hopefully escape and then get something somewhere here and reach the global minimum, which is here. Now, this is a very hopeful case, right? And this does not really happen in practice, but we don't have any other choice but using mini-batch gradient descent, because in deep learning, we have large data sets and the data is of high dimensions. So we are going to use SGD or mini-batch gradient descent in any case. So there are advantages to using it. And it's not always bad. Okay, let's go back. So since we are going to use SGD or mini-batch gradient descent, and then we are going to add something to our optimization in order to get to this, in order to converge. So the idea is that we are going to reduce the learning rate gradually, and this is called learning rate scheduling, and we will discuss this towards the end of this tutorial. And basically, this is going to be one part of our recipe for training deep neural networks, and this is super important. It has a lot of effect. It has a very great impact on the optimization, and we are going to use schedulers, and this is going to be part of your toolbox. Now, it's very subtle art, right? We don't want to reduce our learning rate too quickly, or we will get stuck in the local optimum, and get stuck, right? So there is some subtleties to how to choose this scheduling of the learning rate, and this illustration. So the algorithm doesn't change much, except that for when we are computing the gradient, we are going to compute it over a batch of m samples, a mini batch of m samples, and when m equals 1, then it's just stochastic gradient descent. And this illustration here pretty much sums it up. So in blue, you can see batch gradient descent, the original gradient descent, and you can see that we have a very nice trajectory towards the minimum. And on the other end, we have the stochastic gradient descent. So in each, we calculate the gradient each time on a single sample. You can see it's very noisy. And when we get around the minimum, we don't stop. We just bounce up and down, and we go around the minimum unless we use learning rate scheduling, unless we reduce the learning rate. So then we can stop around the minimum. And in between, we have mini batch gradient descent, which is we only calculate the gradient over a portion of the data and not the entire data set. So it's something in between SGD and batch gradient descent. And this is usually what we're going to do. And you can see that the trajectory is less noisy. And again, we are going to use learning rate scheduling in order to converge and nicely stop at the minimum. Okay. Now, actually, I just want to add that in deep neural networks, sometimes using a smaller batch size actually leads to better performance. And so you'll see that it's not always bad, that the fact that we can use the entire dataset to calculate the gradient, but it also helps us in some cases. So let's summarize. So we have batch gradient descent, stochastic gradient descent, and mini batch gradient descent. So they are both, all of them are good, okay? So, and in practice, we don't have any other choice in deep learning but to use mini batch gradient descent. The update speed, so slow, fast, medium, and we will discuss the update speed in a minute, and we will also stand on the difference between two terms, iteration and epoch. Memory usage, so batch gradient descent requires us to calculate the gradient over the entire dataset. And as I've just mentioned, sometimes it is impossible. So it requires very high memory. And on the other end, we have stochastic gradient descent, which requires us to calculate the gradient over a single sample, so the memory footprint is quite low. And in between, we have the mini batch gradient descent, which is medium. Now, online learning. So what does online mean? So think about real life applications. We have big corporations that continuously train on our data. So consider a social media network, and on this social media network, users there are new users every day. So we need to add their data to our pool from which we train our models. So of course we are going to train on the user data, and we need our algorithm to support online training. This means that they support the idea of data streams. So basically, new samples arrive all the time, and we need to add them to our pool of data. So online learning is impossible in batch gradient descent because the dataset keeps getting larger, right? So it grows larger, and at some point our memory is limited, and we won't be able to calculate the gradient over the entire data. And on the other end, of course, in stochastic and mini-batch, it's possible as long as the size of the mini-batch is not too large. Then we can support the dataset getting larger because we anyway don't calculate the gradient on the entire dataset, so it's possible. Now, here is an important thing that we emphasized in the recap tutorials. All gradient descent algorithms, they require scaling if the features are not within the same range. So what does scaling mean? So remember that we have something called pre-processing, where we pre-process our data and prepare it for training. And what we want to do is we want to bring the data to be of the same scale. Now we'll take a look at an example in a couple of minutes, but here is the breast cancer dataset we used in the previous tutorial. And you can see that we have different features, and the features are of different scales. So for example, the radius mean, you can see that its scale is much larger than the concavity mean. Right? Now, this greatly affects the gradient descent process, and we will see an example in a minute in the linear regression problem. But what we actually want to do is we want to rescale these features. So usually we use like minimax normalization or standardization, where we bring the scale of the features to be of the same scale. So in minimax between -1 and 1, and in standardization we bring it to be like we sample them from a unit Gaussian. So we bring them to the scale to the range of between usually -5 and 5. This is what happens when we standardize. Okay, this is a bit later. So let's talk about the update speed. I owe you an explanation on that. So here we are going to pay attention to the difference between two very important terms in deep learning. The first one is called iteration, and the second one is called an epoch. So an epoch, one epoch means that we passed over the entire dataset. Okay, so when we perform batch gradient descent, then one epoch equals one gradient update. But what happens in mini batch gradient descent and stochastic gradient descent? Then we actually don't perform an update based on the entire dataset. So we define something called an iteration. So iteration is a gradient update. So every gradient update is an iteration. Now note that except for batch gradient descent, iteration is not the same as an epoch. In a single epoch, we are going to have many iterations. So let's see an example. So let's say we have m samples, so m equals 100, and we wish to train for 10 epochs, n equals 10. So n is the number of passes we are going to do over the entire dataset. So our algorithm is going to see the entire dataset 10 times. Okay, now we're going to have a batch size of m, and batch size and number of epochs are something called a hyperparameter, which are parameters that are chosen by the user prior to the training stage. They are not learned. They are going to be tweaked and tuned by the user, but they are not learned as part of the training process. So we will see many types of hyperparameters. In here you can see the num epochs and batch size, but the learning rate is also an hyperparameter. And we will meet this a lot later in the course. So let's do an example. So for each method, let's calculate the number of gradient updates. And gradient update is going to be an iteration. So this is, you can imagine a for loop and in this for loop, we are going to have an inside loop where we perform gradient update. So for batch gradient descent, M, the batch size is equal the entire dataset. So M equals the capital M. So this division here is just 1. So the number of gradient updates is 10 because in each epoch we have only one gradient update. So one gradient update in each epoch, this means the update speed is quite slow, right? Because there are only 10 updates. Now for stochastic gradient descent, M equals 1. So this division here is going to be 100. So it's 100 divided by 1. And N is the number of epochs, so 10. So we are going to have 1000 gradient updates because in each epoch we are going to perform, we are going to compute the gradient 100 times, right? And this means in each epoch we are going to see we are going to have 100 updates, and total we are going to see 100 updates because this multiplication here gives us an. So you can see that the update speeds, the number of updates is very fast. We have a lot of gradient updates. And in between we have mini batch gradient descent, so M equals 10, and we have in each epoch we are going to have 10 updates. So in total we are going to have 100 updates, so this is why it's medium. Now, why this is important? So the update speed affects how we tune the other hyperparameter, the learning rate. Because if we have only a few updates, very low number of updates, then we can use a large learning rate. So the step size we are going to use for gradient descent can be larger. On the other end, when we have so many updates, then we should carefully take a look at the learning rate and maybe pick a lower learning rate so we can converge nice and slowly into the minimum. So it's very important. I hope this is clear, and this is going to affect our optimization later when we are going to talk about larger neural networks. So there are a couple of challenges. And one of them is picking the learning rate. So hyperparameter tuning is a very big part of deep learning. And of course, once we decided on a learning rate and we're going to use mini batch gradient descent, then we have to define the learning schedule. We'll talk about this a bit later. Now, another challenge is feature of different scales, but this is easily solved usually with normalization or standardization. And finally, since we are going to work with real-life data usually, then and the functions are going to be very complex and not convex, and we are usually going to end up in a local minima, and there can be many local minima, and this is not always bad. Okay, so some local minima can be equally good, but just keep in mind that we are not optimizing. We won't be getting to the global minimum. So let's talk about the learning rate, and I'm pretty sure I emphasize that it's important, but let's see why. So the learning rate is the step size of the gradient descent, this alpha or eta, and if we are picking a too small learning rate, then we have some convergence guarantees for gradient descent in the very simple convex case, but if we pick a learning rate that is too low, then it requires many updates before reaching the minimum point, and sometimes this number of steps required is so large that we don't have this time to wait. So basically, it's not good. On the other end, we have to when we pick a too high learning rate, then the training dynamics are going to bounce up or down, and you can see the loss function, for example, up and down, going up and down, and usually, so as you will see in the lectures, loss function must go down. So if the loss function during training goes up, this is usually a red flag and a bad sign, and usually it's a sign that you picked a too high learning rate, so you need to go down. Now the art is going to be finding this just right learning rate, and we will see all the tools in our box that we can use in order to find it. So in practice, this is what happens. So you can see here a real optimization of a function. And you can see that when you use a very high learning rate, then the training diverges and jumps up and down and misses, and it can miss the minima. Okay, so let's do a practical example, and I'm going to reiterate the example from the recap tutorials. So let's talk about linear regression for a minute. And then we'll end the tutorial with talking about with discussing scheduling. Okay, so here's our problem. So we have values y, our target values. We have x, our input features, and we have n examples where each example has L features, and we want to find w, some parameters to be learned, the weight for each feature. And if you recall, then when we do regression, then we optimize the mean squared error, the MSE, and this is related to also to maximum likelihood estimation, as we explained in the previous tutorial. So check that out if this means nothing to you at this point. And okay, so we want to optimize this problem. So we want to find the optimal W that minimizes the distance between our predictor. This is X multiplied by W. This is our prediction for the target values Y. And we have the ground truth values, and we want to minimize the distance. So for linear regression, we have an analytic solution, right? We can do the pseudo inverse. So it requires us to invert the matrix and find the optimal W like this. Now, this is usually impossible because inverting a matrix requires a lot of calculations, and the dataset can be very large, and L can be also very large, the number of features. So we are going to take the gradient and do this iteratively with gradient descent. So the gradient is just this left part here. Okay. Now notice a very important thing, and this is the scaling issue. So if you take a look here, you can see that the gradient, which is this left-hand part here, it is directly dependent on x, which is the original features. Now, since this is part of the gradient, and we are going to take a step in that direction. Now, if x, which has different features of different scales, then the step we are going to take is effectively determined, the effective steps of each feature. Effective set of each feature is directly relied on the scale of the feature. So if we have a feature that is at a larger scale, then the gradient, the effective step size we are going to take is going to be larger. Now this means that we are going to go in the direction of the features of larger scales. Now this means that if we have concavity mean and texture mean, for example, then texture mean will pull the optimization stronger to its direction. Now this effectively means that we assume that texture mean is more important than concavity mean for our target values, to predict our target values. But this is not necessarily true, right? Because maybe concavity mean is more important, but because we did not rescale our features, then this is larger. And when we take a step in that direction, then the effective gradient is going to be larger, and the optimization is going to be mainly governed by this feature here. So it's important to standardize or normalize these features so to be of the same scale. I hope this is clear. Okay, so what we're going to do is we're going to implement batch gradient descent. So we can see the gradient right here. So the 2 here is not required. You can just eliminate it, and this is just a scaling that is part of. We can treat it as part of the learning rate, so it's not critical. But for simplicity, we just use it here. So here is the algorithm. So the first thing we do is scaling. So here we are doing standardizing. Okay, so basically we subtract the mean and divide by the standard deviation. Now note that in practice we talked about this in the previous tutorial. We only apply the scaling, and we calculate the scaling parameters, in this case the mean and the standard deviation, over only the training set, right? And we apply the standardization with the same parameters to the test set. So in order to preserve or to prevent data leakage from the test set to the train set, then we calculate the mean and mu the mean and STD only on the training set and apply it on the test set. So keep that in mind. We talked about this in the previous tutorial. So here it is, very simple, very short. So we are going to go over our data 10 epochs. So this is the external for loop. And inside this loop, we have the iterations, the gradient updates. So we're going to go over all of our batches, right? So in the case where the batch size is the same of the same size of the entire dataset, then we just have here we are going to have a single iteration, and the number of updates will be 10, just like we discussed before. So we can see here we implemented exactly the rule from the pseudocode, right? So it's very simple. It's a very simple model. And basically, you can see that we are going to use matrix multiplication. This is the at sign here, and this is exactly the equation here. Very simple. We run it, and you can see how W's are tweaked over time, right? At some point, they don't change very much, okay? And we can print the final values, and we can also plot our prediction, which is as you recall, our prediction is x multiplied by w. So this is our prediction for the target values, and we actually have the ground truth value y, and you can see here that our prediction is pretty good, right? So you can see that in areas where we have a lot of data, then the prediction is good, and in areas where we have sparse data, then prediction can deviate a bit. But it's overall a very good solution. Okay, now let's end this tutorial with something which is probably new to you if you've just finished the machine learning course, and this is what we talked about, the learning rate scheduling or annealing. And this is super important, and we are going to use this always when we are optimizing deep neural networks. So let's see what this means. So when we are going to train deep neural networks, it's usually helpful to anneal. Annealing means gradually changing the rate of the learning rate. So basically, we are going to start with some learning rate and slowly decay it, so it goes to 0. And hopefully, once the learning rate is very low, we hopefully have already reached to the area of the local minimum, and we can converge nicely into it. Now, this is all wishful thinking, right? We hope that it happens, and sometimes it requires a lot of tuning and finding the right scheduling. So this is what we're going to do next. Now, there is some physics intuition here. I like it, so let's go over it. So you can think about a system with particles, and with high learning rate, the temperature can be high. So the particles contain a lot of kinetic energy, and they are erratic. They move around a lot, bounce up and down, and they cannot settle and down into deeper and narrower parts of the loss function, right? So basically, we are going to see this noisy dynamics. Now, knowing when to decay the learning rate can be very tricky, right? So this is what we talked about earlier. If you decay it slowly, you will be wasting a lot of computation, bouncing around with little improvement for a long time. So this is the part where the learning rate is too high. But if you press the brakes too aggressively in the beginning, so the system will cool quickly, and we will go back to the regime where we are in a slow learning rate. So we want to find the interpolation threshold where we go down, where we find the just right learning rate. So there are a couple of very popular schemes to implement learning rate decay, but the very simple one are going to be covered here. Now I'll just note that there is a recent trend where we have actually cyclic learning rate schedulers. You can press on the link here just to get here to see something called one cycle learning rate scheduler. It is also implemented in PyTorch, but the idea is that at first we are going to warm up the learning rate. So we're going to start with a low learning rate, then increase it until some point, and then go down. So this is one cycle, right? And we can have multiple cycle. This is implemented usually with something called cosine scheduling. So let's talk about a couple of schedulers, and we are going to use them a lot. So listen carefully. So multi-step decay, the very simple idea is just to reduce the learning rate by some factor every few epochs. So so this is another hyperparameter. So for example, you determine that you want to reduce the learning rate by 0.1 every 20 epochs, or for example, you can give it a list of epochs. So I want to reduce the learning rate at epoch 5, 15, and 100. Okay, so this is very simple. And we'll talk about a heuristic where we don't need to set the number of epochs manually. We can just use a heuristic for when to reduce the learning rate. I'll talk about it in a minute. Another idea is doing it more continuously. So we can use exponential decay. So basically, the learning rate is the initial learning rate alpha 0 multiplied by exponential of k multiplied by t. So k is a hyperparameter, usually called the temperature or gamma, and t is your scheduling unit. So t can be either an iteration, a gradient update, so every batch, and t can also be an epoch, right? So it's up to you. And usually we are going to use units of epoch. So this is the widely popular case, but you can also use an iteration. So you can reduce every iteration. 1 by t decay, very similar to the exponential one, but instead of an exponent, we have 1 plus kt, and similarly k is some hyperparameter. Now finally, there is something called cosine annealing, which is it can be cyclic and it can also be decaying. So it has its applications usually in something called transformers, but we'll see this later in the course. Now, if we take a look for example, let's look at the 1 by t. So as training continues, so as t grows larger, so as the epochs increase, you can see that the learning rate, the initial learning rate, is decreased, exactly what we wanted, right? Now picking the right k in this case can be tricky, and a lot of trial and error is required. Now in practice, my favorite and my recommendation to you all is to start with a step decay, the very simple one, okay? So the idea is that we give it a list of epochs where we want to reduce the learning rate, or just reduce it every epoch by some constant fraction. So for example, you can reduce every epoch by 0.99. So this means that we decay the learning rate very slowly until it reaches 0. Okay, so in PyTorch, all of these are implemented, right? So I recommend starting with the step LR and then maybe the multi-step LR. They are very simple. We have the structure here. I will talk about, in the next lesson, I will do an entire example of how we incorporate the scheduler. It's very simple. Okay, so we will define the scheduler, okay? And after each epoch, at the end of each epoch, we'll just advance the scheduler to the next step, okay? And I'm going to finish this tutorial with a heuristic called reducing learning rate on plateau. And the idea is to use a gradual step decay, but we are going to, instead of predetermining the number, the epoch number, we are going to use a heuristic, and this heuristic is going to help us determine whether we should decrease the learning rate. And the idea is that in supervised learning, which is the focus of this course, we are going to use something called a validation set or test set, where we measure or evaluate our performance. Now, what we usually see, for example, in classification, in a supervised learning problem, we can see that at some point, the loss function or the accuracy does not increase. So we reach something called a plateau, just a straight line. Okay, nothing improves. Okay, so when nothing improves, so it means that we are going around the same point of the loss plane, right? So this is a good sign that we should decrease the learning rate, because maybe we are already around the minimum, but we have too much energy and we need to reduce it. So the idea is that you should you set some patience parameters. So patience means how many epochs, how many iterations, or how many iterations should I wait where I see a plateau, and then I reduce the learning rate. So this means that the scheduler reduce learning rate on plateau. You can see you can click here and see the input parameters. So for example, if you tell it to wait 1 epoch, then it means that we will see in the learning curve that we reach the plateau, and then the scheduler waits 1 epoch, and then it reduces the learning rate. So this drawing here can help us understand what happens. So let's begin with the reduced learning rate plateau, which is the pink curve here. So what you can see is that we around this area here, we reach a kind of plateau because the training loss has not improved, right? Or on the other end, the test accuracy has not improved. So basically, when we do not improve, it's a good sign that we should reduce the learning rate. So basically, we take a step, right? And the step size, where how much we reduce the learning rate, is up to you. And you can see here that after we reduce the learning rate, then we got a bump in the performance, which is good, right? However, since again we reached another plateau, this scheduler kept reducing the learning rate, eventually reaching 0 and not improving anymore, so it gets stuck. Now, why am I telling this? So people like to use it. It's a good heuristic for supervised learning. However, it's not usually the best one. And as I recommended you, the step one, we will see them in a bit. They're usually simpler and work better. So it's up to you. If people like using it, this is what implemented in the example below, but I really recommend starting with the simple one, which is step 1. So let's take a look at when we don't reduce the learning rate at all, this is the blue one. You can see that it's bad, right? But when we are using 1 milestone, so 2 milestones, so 1 milestone, it means that we give the multi-step scheduler 1 step. So for example, reduce the learning rate at epoch 30. Okay, so this is one milestone, and 2 milestones means that we, for example, say reduce it epoch 30 and also reduce it epoch 100. Okay, so if we take a look at here, so you can see the first milestone. The first milestone is right here, right, and you can see a great decrease in the training loss, and consecutively an increase in the testing accuracy. Now here is the fine print. So take a look at. So we are looking at the red and the green one, and you can see that for the green one we have another milestone. So it's very hard to see, but it's right around here. And the second milestone gives us another slight bump in the performance. So this is the art of finding the right scheduling, right? So eventually, the green one was the best overall. Okay, so this is what we want to achieve. So this is why I'm recommending you to start with the milestones one, with the step scheduler, which is one of these two, step or multi-step, choose between these two, and see how it goes. So we'll talk about the really interesting stuff in the next tutorial, but before we end, I just want to show you the recommended videos part. So anything we discussed here, there are very recommended videos from YouTube. You can take a look here if you want to extend your knowledge. And finally, if you want to dive deeper, there are more references here. Okay, that's it for now. Thank you. Thank you for watching, and we will see you next time. Bye now.